Hello there. One of the first analysis techniques you're going to learn is a z-score. And the first thing we need to know is how to calculate a z-score. Z-scores are fairly straightforward in that the formula is just z is equal to x minus mu over our standard deviation. This means that we take the value we're looking at, subtract the mean, and then divide by our standard deviation, which will give us a value that tells us where our x, our value, falls in the distribution and tells us how unusual that value is given the data we have in terms of our mean and standard deviation. Once we get through calculating our z-scores, I'll go ahead and show you how to get information from a z-table to talk about the proportion of our z and the percentage of the z. So let's begin by relying on the data set we've been using thus far of 3, 3, 5, 8, 10, and 13 with mu equal to 7. That's all solid. So here we go. First thing we have to do is add our variables, or rather our values, into this formula. So let's take a look at one of these. I think 13 will be an interesting one to look at. So let's take z is equal to 13 minus 7 over our standard deviation. Our standard deviation, we'll add it in over here, equal to 3.7. Over 3.7. That's step 1. Step 2, we come down here. We still have z is equal to, in this case, we have 6 over 3.7. We take that, we calculate it, 6 divided by 3.7, and we end up with step 3. Z is equal to, leave this in the frame for you, 1.62. So that's interesting. It gives us a way of seeing how odd our variable is, that x is. However, there are some things we need to know about it while we interpret it. The first thing we need to know is that with mu, if we were to plug mu in here, we would be dividing 0. So if we're looking at mu, mu has a z-score of 0. That's our first piece. Our second piece is that each increment of 1, either positive or negative, indicates how far the data point is from the mean in standard deviation. So 1z is equal to 1 standard deviation. We can see from our score of 1.62 that we are over 1.5 standard deviations above the mean. We can tell that because of 0.3 positive z means our data is above the mean. While negative z means below the mean. We'll go ahead and separate these out just for some extra clarity. So with that being done, let's go ahead and take a look at calculating the proportion and percentage of our z-score. To do that, we're going to take this, move it out of the way, and I'm going to go ahead and bring in a textbook that has statistical tables at the end. So here we are. This book has it as table A1. However, it could be in different places in different textbooks. How this is set up is that we have a column for z incrementing by 0.01 all the way from 0, 0 all the way over here on the third page to 3, at which point they give token values for 3.2, 3.4, 3.6, 3.8, and 4. This is a holdover, and this whole table is a holdover from when we didn't have computers that were powerful enough to calculate exact z-scores and where they fell for us. So we're limited to hundredths as our increment. So our z-score was, if you remember, 1.62. So let's go ahead and find that. That will be on the second page. As we roll down here, 1.41, there we are, 1.62, which has a beyond z of 0.0537. That means that if we take that proportion, that 0.0537, we'll get this out of the way, label that beyond z. That tells us that out of the proportion of 1, this is how much is above z, is a score that is greater than z given our mean and standard deviation. And in fact, if we were to take 1 and we were to subtract 0.5, because z is measured from the mean. And since we were looking at a positive score, maybe out here somewhere, let's put 1.62. Since we were looking at this, this measures the proportion over here. This is, let's get a different color. This area here is equal to our 0.0537, which means this area, let's grab another color again, which means this area in green is equal to 0.5000 minus 0.0537. We can calculate that as 0.5 minus 0.0537, which gives us, which is also equal to 0.4463. And I don't round these because it's a z-score, at least not as I'm demonstrating things. It's up to you when you make decisions for your data. However, this means that we have this whole part that's unexplained. Let's grab my last color. We have this. This is equal to 0.5000. It's the whole area below the mean. So this means that the z-score of 1.62 is above 0.5 from here, the area that's below the mean. So we have our 0.5000 plus the difference between the 0.5000 above the mean and the area that's beyond our z, which was this, our 0.4463. Move that up here, 4463, which tells us we have 0.9463. So that's the proportion of scores that a score of 13 is greater than in this example data set. If we wanted to turn this into a percentage, all we have to do is multiply by 100 to give us, we'll move it over here, 94.63. So in this data set, a score of 13 is greater than 94.63% of scores, or we could say is at the 94th 0.63 percentile. This covers the majority of what you need to know about z-scores. In order to keep this from getting too long, I'm going to save the last bit where I talk about how to convert from a z-score into a raw score, so the reverse of what we did here, in the next video. I hope this is helpful for you as you're going through your statistics classes or are looking stuff up for your research. Let me know if you have any questions about this. This will be available in the description